Our environment holds many stories of climate change. They are stored in what we call climate archives. Tree rings, for example, ice cores, marine sediments, and speleothems. Let's take a closer look at speleothems and why they are a special kind of climate archive.
They are very unique because we can find them all over the world, and unlike, for example, ice core records, they can also tell us something about a local climate signal.
Speleothems, which are also known as stalagmites or stalactites, are geologic formations that can be found in calcareous caves. They can be accurately dated through radiometric methods, yielding high-precision chronologies for climate reconstruction. In addition, they can sometimes form successive annual layers, much like tree rings. These layers can be continuous on timescales of decades to millennia, which make them unique terrestrial climate archives.
But then there are also other isotopes and other elements that we can measure in stalagmites, and by looking at how the concentration of these isotopes varies, we can learn something about past climate variability.
But how can this information about paleoclimate be accessed? And what does radiocarbon have to do with it? Typically, information about paleoclimate is acquired by drilling into the stalagmite and then executing, for example, a mass spectrometric analysis to access information about the isotopic and elemental composition. Stable carbon isotopes in speleothems have been extensively measured in the past. Unfortunately, the interpretation of the stable carbon isotopes is very difficult. This is because the carbon isotopic composition is strongly modulated through many chemical and physical processes in the soil, host rock, and cave. Radiocarbon, however, can help us overcome this difficulty, as it can be used to distinguish which of these processes were more or less important when the speleothem formed.
So there are three naturally occurring carbon isotopes. On the one hand, there are the stable isotopes C12 and C13, and they make up most of the carbon that we find. But there's also radiocarbon, which is a rare isotope. It's radioactive and it's produced in the upper atmosphere, and it's very valuable to us because of its radioactivity.
In the host rock that formed millions of years ago, all radiocarbon has decayed. In contrast, soils have radiocarbon concentrations often relatively close to that of the atmosphere. Looking at the stable carbon and radiocarbon signatures can help us disentangle the different sources and processes that affect carbon in speleothems. So far, however, radiocarbon analyses have been rather time-consuming. At ETH Zurich, a worldwide unique laser-based sampling technology for rapid high spatial resolution C14 analysis in carbonates has been developed.
So the novelty about our research method is that we use a laser for radiocarbon analysis. So what we do is we focus a laser on the sample surface, and the laser reaches a very high energy density. So the carbonate is evaporated and parts of this is converted into gas. And this gas we can directly feed into the AMS, where we do the radiocarbon analysis.
By scanning across the sample, the concentration of radiocarbon within the whole speleothem, which might cover millennia, can be assigned within hours or days. Conventional methods require weeks or months to do so. With Laser Ablation AMS, near-continuous datasets can be generated covering up to 10 cm long specimens, while attaining a spatial resolution down to 100 Hence, stories about our climatic past can be uncovered at unprecedented temporal resolution.